Today in class, we talked about two different topics. We've been talking about weak acids, and we kind of talked a little bit about weak bases. Now we're going to talk specifically about weak bases and then something called a salt. So we learned to do two different things today. One example of a weak base is ammonia, NH3. Now, the weird thing about ammonia is it doesn't have a hydroxide. So if we were thinking about the Arrhenius definition, where is the hydroxide coming from? Because ammonia is a base. So when you have ammonia, you have to write water. And if you put ammonia in water, and if you think of water as HOH, hydrogen hydroxide, basically what happens is one of the hydrogens comes off of the water molecule and actually attaches itself to the ammonia. And when that happens, it technically makes ammonium hydroxide, but in solution, what it does is it gives you ammonium ions. So this was no charge, and it picks up a hydrogen, which has a positive 1 charge. So now it becomes a positive 1 aqueous solution, and then we get hydroxide. So there is our reaction. So anytime you have a base that you know is a base, you need to put it in water, and then you're going to break it apart. Basically take one of the hydrogens off. Ammonia products are the hydrogen's going to go in the back. And then we have a compound called an amine. And what an amine group is very similar to an ammonia compound, but instead of having 3 hydrogens, one of the hydrogens has been replaced with a carbon group. So if we had something like this where it had nitrogen and it had 2 hydrogens, and I'm not going to draw it extremely correct, but and it had a carbon connected to it instead of that hydrogen, this is called an amine. And when we get into organic at the end of the year, we'll talk a little bit more. This right here is our amine group. It's basically an NH2 group stuck on a carbon. And since this is 1 carbon, the prefix for 1 carbon is meth. And so this is actually called methylamine. It's also a base. And so we need to recognize when we have an amine group, so you're going to see a carbon and then you're going to see an NH2 if you saw something like this. And of course I'm drawing them out the organic way so you can kind of see it. Again, not exactly correct organic wise, but if you saw 2 hydrogens, I meant to say 2 carbons attached to it, the prefix for 2 carbons is eth. So this would be an ethylamine. If you had 3 carbons, it'd be a propylamine, and so forth. These are going to be bases, and when you get into biochemistry and stuff, you start to see that more. So when we write these things, because you don't have a hydroxide, but they are bases, so all amines are bases. Because you don't have a hydroxide, you're going to have to put them plus water as well. And you're going to see the same thing. You're going to see the hydrogen coming off, and it's actually going to attach itself to the end of the molecule. So we'll go to our slideshow presentation where you'll see how it's actually written. And writing them is kind of the hardest part for some of you. It says many weak bases do not have hydroxide. This means that water must be included when writing the formula. Many weak bases contain nitrogen, such as the ammonia. Amines are related to ammonia where one of the NH groups is replaced by an NC group. And so here is the methylamine that we just saw. CH3 is the methyl, and then there's the amine. So if we were to try to write this equation, we would put it in water, and it's just like before, the HOH, and one of the hydrogens is going to come off, and it's going to actually attach itself to the end of the molecule. So you have CH3 now becoming NH3, but it's going to have a charge because it was a compound with no charge. It picked up a hydrogen, essentially a proton, and becomes a positive 1, and then water is left as OH minus. And then before in our conversation, we actually had talked about acids and conjugate bases, etc. So this is a good point to kind of review. If we know an acid, for example, we'll go with acetic acid. There's an acid. Well, its conjugate base would be the same thing with the hydrogen removed. So this is a conjugate base. C2H. So when we took that hydrogen off, we get that ion. So if you get something like hydrochloric acid, its conjugate base would be the chloride ion. If you get something like hydrofluoric acid, the conjugate base would be the fluoride ion. So you kind of got to understand that because we're going to be talking about acids and bases and sometimes conjugates, and being able to recognize, oh, that's a conjugate base, is going to be kind of important. And so that leads us to the next. Anions or weak acids are also known as weak bases. They're, for example, this is ClO minus 1. If we put a hydrogen on it, we would see that we would get hypochlorous acid, which is a weak acid. So because we know this is a base, we're going to put it in water. And notice what happens this time. Instead of the hydrogen coming off and going on the end like it did with these amines and ammonia, the hydrogen comes off and goes on the front. And we essentially get the hypochlorous ion, and then we get that hydroxide. Because this is a base part, not the acid, this is the acid, or technically the way this is written, this is the conjugate acid, and this is the base. When we did all this stuff here, so you kind of can think, because the arrows again are going both ways, so here's the acid, that's conjugate base, or vice versa. So we just need to start recognizing those anions, and if we stuck a hydrogen on it, would it be with a weak acid? So that's kind of important for us to write the equation, but we're going to see it Kb because that is the base instead of Ka for an acid. Whoa, wrong button. So now we're going to move forward. So it says calculate the pH and the hydroxide concentration of a 0.035 molar solution of ammonia. Now actually doing the problem itself is not hard. Most students really just have a hard time writing the equation. You have to know that ammonia is a base, so you're going to have to put it in water because there's no hydroxide. We're going to draw that double arrow. We're going to make ammonium and hydroxide. Essentially that water molecule is breaking up and the hydrogen moving. We're going to write it because it is a weak base. We're going to set it equal to Kb instead of Ka. Water is a liquid, and pure liquids we don't care about as far as, well, it's really important to have water, but as far as the Rice equation, we don't put pure liquids in the equilibrium expression. So you get 0.035 molar, you get 0, 0, because these are all 1 to 1. Don't you love this chapter? It's all 1 to 1. You're going to add x. Don't get it comfortable because next chapter it won't be that way. And add x. We're going to subtract x. 0.035 minus x. And we'll end up with x squared over 0.035 minus x. And we're going to equal it to a Kb because of this hydroxide. I want to circle that for we can make sure we pay attention to that. Because anytime you have hydroxide floating around there, it's always going to be to a Kb, and that's going to be a huge thing in next chapter to know what to set it equal to. Alright, so we can get rid of our minus x. You could use solver, whichever you prefer. I think I did it both ways. You get really close to the same answer. If you scratch through your minus x, because this is to the negative fifth, you get 7.94 times 10 to the negative fourth. Or I think if you use solver, you get 7.85 times 10 to the negative fourth. I usually work it both ways. Now, if we follow x, one of the questions is what's the hydroxide concentration? Well, x, I don't know why I have those pluses there, but our x is our hydroxide. So there's our hydroxide concentration, so either one of those. And now to find the pH. Well, that's hydroxide, not hydrogen. So we have to find the pOH first by taking the negative log of our x and then subtract it from 14 to get our pH. And so our pH should be 10.89 or 10.90 depending. When you do this one you get 3.11 or 3.10 depending on which x you use, but really close to the same number. So not hard. The hardest part of that is actually writing the equation. Same thing with the amine. Same process going on. It's an amine. You have to recognize an amine is not an acid. So the hydrogen's not going to come off. You have to put it plus water. And what happens? The hydrogen goes to the end. Oh, I already put that hydrogen on the end. Did y'all see that? Let's get that little 2 in there. It was a 2. It picks up a hydrogen, becomes a 3, and then it makes that hydroxide. It's going to rise just like, so again, these aren't really any harder. The hardest part is writing those equations. So 0.075, these start out as 0, we subtract x, add x, I meant to say, add x, subtract x on this side. Always where your 0 is, you would add. So we end up adding x squared over 0.075 minus x. We're going to set that equal to Kb because of this hydroxide. And so then this would be 4.4 times 10 to the negative fourth. Negative fourth a lot of times isn't very safe to use solver. I think this one would have been okay. I mean, it's always safe to use solver, but not okay to scratch through your x. I think I used solver and did it the other way, and you actually get about the same answer. I got 0.00, and there's only 2 sig digs in this problem. So there's my molar. That is your hydroxide. So that is your OH concentration. So you can find the POH by taking the negative log. And then your POH, I got about 2.26. So your pH is 11.74. So it's actually pretty high pH. You could find your percent ionization if I asked. You could take this x divided by that I times 100 to get your percent. Same with this one up here. We could take our x divided by I times 100 to get our percent. So that's pretty much all there was with weak bases.
Alright, the first part of this is just has pH plus POH equal 14 and hydronium times hydroxide equals 1 times 10 to the negative 14. There's a relationship between the Ka for an acid and its conjugate base, which is the Kb. If you multiply those K's together, you'll get Kw, which is that 1 times 10 to the negative 14th. And you can actually figure out which acid is stronger by looking at the Ka values. The larger the Ka, the stronger the acid is. So on this first question, I'll go ahead and click all of the questions. That way I can write and then... Alright, it says given that the Ka for acetic acid is 1.8 times 10 to the negative 5th and that of hypochlorous acid is 3.8 times 10 to the negative 8, which is a stronger acid? So all you have to do is say, well, which one of those numbers are bigger? The bigger the number, the stronger the acid. And our stronger acid is going to be this, because it's to the negative 5th. This goes to the negative 8th, so the acetic acid is a stronger acid. This question says, find the Kb for, notice that this is the conjugate of acetic acid, this is the conjugate of hypochlorous acid. So to find the Kb for this guy, I would take 1 times 10 to the negative 14th, and I would divide by 1.8 times 10 to the negative 5th. And you would find that it's 5.6 times 10 to the negative 10th power. I do the same thing for this one. Oops, 3.0 times. And you get 3.3 times 10 to the negative 7th power. So those are my answers for number 2. Very easy to do to go from that. It says, which is a stronger base, the acetate ion or the hypochlorite ion? And it's not going to be a strong base, but it's a stronger, more basic counterpart here. And again, it's going to be the one with the larger number, so that is going to be the hypochlorite ion. So if you'll notice, the stronger the acid, the weaker its base. And the weaker the acid, the stronger its base. So that's how you can tell. So you could have actually be able to answer question 3 without having to do part B. I just wanted to show you mathematically. So the next part of this PowerPoint says the stronger the acid, the weaker its conjugate base, and vice versa. Okay, definition of a salt is a product of an acid and base reaction. So salt is pretty much an ionic compound that's formed from the cation of an acid, the cation of a base and the anion of an acid. And all salts do something called hydrolysis, and that's what's going to give us a little bit of trouble in Chapter 17, but we're going to be okay with it. And we can kind of predict the pH of an acid or a base by looking and kind of figure out maybe what formed it. If a salt is formed from a strong acid and a strong base, then it's a neutral salt. For example, NaCl, I'm just going to click all of these before I can write. NaCl is a product of, I can go over here for this one, probably sodium hydroxide. The first part, the cation, comes from a base, and this is from the acid part, which is HCl. So this is a strong base, this is a strong acid. If they're both strong, then this is a neutral salt. If we look at this one, we've got LiOH probably was the base that formed it, and then HNO3, and again that is strong, so therefore it's a neutral salt. This one here, probably NaOH, and HCl, which is hypochlorous acid. This is strong, but this is weak, so therefore this is a basic salt. This one probably came from barium hydroxide and acetic acid. So this is a strong base, a weak acid, so it's basic. This one's unique, probably came from ammonia, which is a weak base, and hydrochloric acid, which is a strong acid, so therefore this one's acidic. So if it's a weak base, strong acid, acidic, strong base, weak acid, basic, strong, neutral. What if they're both weak? Well, if they're both weak, you actually have to look at the Ka and the Kb, and whichever one's bigger would decide whether it's acidic or basic. So if it were been made from two salts, you would have to compare the Ka of the acid and the Kb of the base, and whichever was a bigger number would be determine whether your salt is acidic or basic. And sometimes they're close to neutral too if their Ks were very close to each other. So we just practiced these examples, and one of the homework assignments is having you do this. So I'll do it very quickly. It is getting close to 5 here. So this would probably be made from aluminum hydroxide and nitric acid. So this would be a weak base, and this is a strong acid, so therefore this one would be a basic salt, more of a base. This one's made from cesium hydroxide, which is a strong base, and hydrobromic acid, which is a strong acid, so therefore this one would be neutral. This one's made from KOH and H2SO4. This is a strong acid, this is a strong base, this one again would be neutral. This one's made from KOH, strong base, and HCN, hydrocyanic acid, which is weak, so this one would be basic. See if you can figure this one out. This one's probably made from an amine, which is a base, and hydrochloric acid, so therefore this one would be acidic. Simple as that. That's not hard. Alright, so let's calculate the pH for the following. Well, first off, work with this one, and then I'll work with that one there. This is NaCl, which, if you broke it down, that's actually a neutral salt. So the pH of a neutral salt is actually going to be 7. I'm going to work through the math very quickly and show you why that would be. When we start with the salt, we're always going to take a salt and we're going to put it in the water. And you're really going to want to you're really wanting to do the net onyx of this. This is going to make the two things that we think made add. So we really think it made NaOH. This is called hydrolysis. It actually goes back and a little bit makes the two things that we think made it. So there's what we think is going on. Put it in water, slightly does this. But we're going to now do net onyx. This would slash because it's a first family. Water's going to box. This is going to slash strong. This is going to slash strong. So now let's just get rid of some spectators here. Let me go to a better chord. This is just going to be a spectator floating around. This is going to be a spectator floating around. So the real equation, that what's really going on is water breaking down. And so if we think about it, first off, if we were trying to rice it, which we could, notice that that's a spectator, I took this out. So that 0.1 molar there is kind of irrelevant. And water's kind of irrelevant too because it's not in the equation. This starts out at 0. Well, if you had x and you had x and you had x and x, there's no bottom. You would end up with x squared. It equals kW because that's water, which is 1 times 10 to the negative 14. So if I take the square root of that, you would find x is 1 times 10 to the negative 7. If you will look to find pH, I need this one. If I took the negative log of that, you would find the pH is 7. So I just proved it mathematically to show you that a neutral salt actually they'll all look like this. They'll all be water and that. Unfortunately, this guy down here is not a neutral salt. So he's going to give us some problems. So let me get this erased. So we're going to start out with NaC. And then we're going to put plus water. And this is going to make HCN. And it's going to make NaOH. And you really do want to do the net onyx of this. So this will slash. This will box. Unlike the other one, this is weak. It will box. And this will slash. So our spectators here are the sodium, and that's it. So when we get ready to rice this guy, we actually have some Cn minus 1 plus water makes HCN plus OH minus. Now the water we don't care about. The sodium cyanate was 0.5, so 0.5 molar. In the beginning this is 0. So you're going to have minus x plus x plus x, 0.5 minus x, x, and x. So we're going to get x squared over 0.5 minus x. And then we're going to need to set that equal to, we got to decide, is it an acidic salt or basic salt? This is a basic salt. It's not a base, but a basic salt. Or you could see, if you do the net onyx, you can see this OH here. We've got to set it equal to KB. So I meant to put on the PowerPoint, but they should give you for HCN, the Ka for this is 4. I think this is right. It could be, but we'll just go with this number for now. And there's a chart, Appendix D in the back of your book. So if you're looking for a Ka or a KB, they're in the back of the book. in the appendix. So, but this is KB, but what they're going to give me is KA. I don't want to use Ka. I'll get the wrong answer if I use Ka. I need to use B because this is a basic salt, not an acidic salt. The Ka is for this thing, but I'm looking for this. It's conjugate. So how do you go from one to the other? Well, you take 1 times 10 to the negative 14, and you divide it by 4.9 times 10 to the negative 10th. We're going to divide those out. You get 2.0 times, we'll just go 2.0 times 10 to the 5th. Times 10 to the negative 5th here. Alright, so now we need to solve. You can use your solver, or you can eliminate that bottom minus x. I'm going to eliminate the bottom minus x just for time's sake here. And I'm getting 0.00316 for my x. It's very late, so I'm hoping that's right. 0.00316. Now if I go back and check, if we've lost our thing what we're doing, we're looking for pH. That's OH. I can't use him. That's not H+. I can't use any of them. But I can use hydroxide. And again, that's one you want to use in Nattonics. So I need to find the POH by taking the negative log of that number. So we'll do the negative log. And I get 2.5 as my POH. So 14 minus 2.5. You'll get 11.5 for your pH. Even though that's a salt, it's got a pretty high pH. And that's how you would work a salt problem.